as you can see, as this is titled, we're going to talk about improper integrals. And the issue with improper integrals is there's some problem with maybe the limits of integration, or some problem with the what we're integrating not being defined within the limits of integration. So there are really two types. So let me just kind of give an example of each type, and then we'll talk in more detail. We might be asked to integrate, say, from 1 to infinity of f of x with respect to x. And so this is one type, of improper integral, that one or both of our limits of integration are either infinity, negative infinity, okay? So we're integrating here, integrating over infinite intervals, an infinite interval. So once again, that means one of the limits of integration is infinity or negative infinity, or they could be have both of those. A second type might be something that looks like this, integrating from 0 to 2 of 1 over x with respect to x. Now, we've really been lazy in the past because we haven't wanted to deal with this issue. But the problem here is, you can imagine that when x is 0, that's the lower limit of integration, then the function itself is not defined. So how can you start thinking about, if we think of this as an area, how can you think about it when the function is not even defined at one of the points, one of the limits of integration? So that's another style. And this is called integrating over a singularity. Integrals over a singularity. Okay, well, and the singularity is that value for which the function is infinite, if you see here, okay? And that would be, or is approaching infinity. 1 over a value that's getting closer and closer to 0 is approaching infinity. Okay, well, let's kind of start from the beginning. And we're going to first concentrate on this type of improper integral. So we assume we have a function f that is continuous over an infinite interval from a to infinity. This is one style, okay? And we'll talk more here in a moment and kind of clarify this a little bit more as we look at the different examples. But assume f is continuous from some constant a to infinity. So for instance, we might have a graph of f that looks kind of like this. I'm just making a suggestion that we might have, okay? Our x-axis is here, of course. And let's suppose this is where a is. Okay, this is the graph of f. Now, and I'm trying to indicate that this function is continuing to the left, but is always going to be above the x-axis. Now, and I didn't say that a was positive or negative. I'm just showing a as a positive value now. So if we were looking at the integral from a to infinity, it would be kind of deciding, well, what's this area that we've got? But the area is open-ended, isn't it? It's closed on one end, but it goes forever on the other end. Well, here's the way we define this. Here's the way we deal with this. We first recognize that we can calculate an integral. So I'm building up to how we're going to do it. We recognize that we can calculate the integral from this value a to some value b that's bigger than a, but it's not finite, okay? So we can calculate that integral. And in fact, we could let that B get further and further away from A, couldn't we? See, we could let that B, let's go way out here. Here's our A value, and let's say our B value is out here. We could let that B value get farther and farther away. And so what we're really thinking about, as B gets farther away, what is happening to the area? And so here's the way we define this in general. We would say that the integral from A to infinity of f of x here, we can't do this at once, but we can integrate from A to some number B that's bigger than A, and we can take the limit of that particular integral, or that particular area, as B gets larger and larger and larger. So that's how we will do this calculation. So an example here, hope I have enough room to do this, is if we wanted to integrate 1 over x squared with respect to x from the value 1 to infinity. But first, let me show you what this graph looks like. The graph of 1 over x squared, of course, is not defined at x equals 0. But for negative x's and for positive x's, the y value is going to be positive, isn't it? So here's really what we're doing. Let's suppose this is roughly where 1 is, okay? And so we're going to integrate this. This is f of x is equal to 1 over x squared. Okay, and so we're going to integrate this from 1 to infinity, which means we're going to find the area of this unbounded region. The region is bounded on the left by 1, but it's not bounded on the right. The region is an infinite region, if you will. So the way we would calculate this, and I apologize, I'm going to come down here and go by this definition, would say, okay, this is equal to a limit. Now, what are we going to do? We're going to integrate from 1 to a value b, 1 over x squared. Now, b is some number bigger than 1, and we're going to let that b get larger and larger. That is, we're going to let that b go to infinity. So what we're going to have to do here is we're going to have to decide what this integral gives us and then take the limit of that result. So we have the limit as b approaches infinity. Now the integral of 1 over x squared is and you can verify this on your own, is the opposite of 1 over x, is negative 1 over x. And of course we had a definite integral from 1 to b, so we need to evaluate that. Now, when we substitute a b in, we get negative 1 over b. And then we subtract, substituting, just up here. We'd have negative 1 over b, and then we'd subtract what we get when we put a 1 in. And I'm just going to simplify that as a 1 minus 1 over b. Well, what's the limit of that expression? Well, of course, the limit of that expression, the limit of 1 as b goes to infinity is 1. The limit of 1 over b as b goes to infinity is 0. So we have 1 minus 0, or the limit value is 1. So what we're claiming here, okay, is the integral from 1 to infinity of 1 over x squared with respect to x is equal to 1. So although that region is unbounded, it actually has an area of 1, which means it's getting closer and closer to that x-axis real quickly, but it does have an area of 1. Well, let's continue this discussion on the next page. So let's get a little terminology under our belts here, and you can see what I've written. If the limit exists, now I'm talking about the limit when we're talking about these improper integrals. If the limit exists, the improper integral is said to converge. So that means, more or less, if the limit exists, the improper integral exists and has a finite value. So that's what converges means, that the improper integral exists and has a finite value. Otherwise, the improper integral is said to diverge. That is, if the limit does not exist, and specifically what would happen is the limit would be infinity or negative infinity. And in that case, the improper integral is said to diverge. That is, the integral results in an infinite, it gives an infinite result. It diverges. So some examples without verification, okay? We just looked at one. The integral from 1 to infinity of 1 over x squared with respect to x, because it's equal to 1, we say that this converges. Okay, because we have a finite limit. On the other hand, the integral from 1 to infinity of x squared with respect to x diverges. Okay, it diverges. If we were to calculate the integral by using this limiting process, we would get a result that was infinity. Okay, so that's the reason we say this improper integral diverges. Now, strangely enough, if we integrate from 1 to infinity, not 1 over x squared, but 1 over x with respect to x, this also diverges. That's strange. It looks very close to what we did as an example. What we would find out is that we get an infinite result there as well. Okay, one additional example without verifying, if we integrate from -1 to infinity, e to the power negative x with respect to x, we will actually get a result of 1. See, we'll have to use a limit. And when we do that, we'll get not of 1, but of e. So we would say this improper integral converges because it has a finite result. Well, what I want to do on the next page is kind of categorize these limits over an infinite interval into 3 types of cases, okay? 3 different situations. And so, and I'll do that on the next page, and then we'll look at a couple of examples, very specific examples. So the first case of integrating where one of our limits of integration is infinity is like we just looked at. First, we have to have a function that is continuous from some constant to infinity, which we have here. And so when we integrate from that constant value, a in this case, to infinity, we create a limit. So we replace the infinity limit of integration with a constant b. And that constant b is some value that's bigger than a. So we can calculate the area from a to b. But we let that b get larger and larger, and that's what the limit is all about. And so that's the way we would set this up. Okay? Let's look at case 2. Okay, in this case 2, we have an interval from -infinity to b, where b is a constant, for which the function is continuous. By the way, I notice I left off continuous on above. So that means we have some value b. It might be positive or negative, but I'm just indicating it with a positive value b. So b is here. And from -infinity up to b, my graph indicates that the function f is, in fact, continuous. Okay? So what we're going to do is that we're thinking of, geometrically, we're thinking of integrating from -infinity. So that's the idea here. We're integrating from -infinity up to this value b of this f of x. Well, we can't integrate using -infinity, but what we could do is we could choose some value of a, and we could always integrate, that a is smaller than b, we could always integrate from a to b. Okay? We can integrate from a, that's our choice, to b. In other words, we're replacing the negative infinity with some constant, some value a. And what are we going to do? We're going to let that a go smaller and smaller. And that's where the limit comes in. We're going to take the limit of this integral as a approaches negative infinity. That's a negative infinity. So that's the way we would set up that integral. Case 3. Okay, this time we have a function that's continuous on the whole real number line. And we're asked to integrate from negative infinity to positive infinity. Well, if this is the graph of f, then we're kind of thinking about finding all of the area that's below that graph. Well, here's what we do in this case. Since this is continuous everywhere, we just choose any number we want to, and we would choose one that's convenient. It might be 0, it might be, we choose some value, some constant, okay? And I'm just going to call that constant c. So I've chosen a value c. What we do is we break this integral in part. We'll say, okay, let's integrate from negative infinity to c, and add to that the integral from c to infinity. And that should give us the final result, shouldn't it? Now, to deal with that, here we use case 2 above, and we go about it that way. Here we use, this is like case 1 above, isn't it? Okay, case 1 above. So to do the integral from negative infinity to infinity means we need to do 2 integrals, and they each will be involved with limits. They revolve back to case 1 and case 2, and we do those separately. They'll each involve a limit. Okay, well let's look at some examples then. So this first example, or this next example that we're going to do, you can see that it's asked us to evaluate the integral from 0 to infinity of the integrand e to the x divided by e to the x plus 1. Or state that it diverges. Now remember, a improper integral will either converge or diverge. And if it diverges, it means that the calculation we create either doesn't exist or is plus or minus infinity, and most likely plus or minus infinity. If it converges, it means that when we do the process and we find the appropriate limit, then we get a finite number. So we don't know the answer to this question until we don't know whether it diverges or not until we start trying to evaluate the integral. So remember how this goes. We can't evaluate at infinity, so the way we set up the integral, is we actually find an integral that we can evaluate. So we can evaluate from 0 to some constant that is bigger than 0. We can do that evaluation. And then we, of course, take the limit of that result as b gets larger and larger, that is, as b goes to infinity. So that will accomplish what we're trying to do. Well, that means we've got to be able to find the indefinite integral. First thing we do is find the indefinite integral of e to the x over e to the x plus 1. And this is a case of a simple process of substitution. If we let u be e to the x plus 1, then du will be e to the x. And so what we actually have here is the integral of 1 over u du. And of course, that's the natural log of the absolute value of absolute value of u, plus a constant integration, but this is going to go into a definite integral, so we don't need that constant of integration. And of course, u is e to the x plus 1. Now, notice here that I'm not writing the absolute values because e to the x is always a positive number. And when we add 1 to that, of course, we still have a positive number. So I don't need to put the absolute values in this case. Okay, so now we've calculated the indefinite integral. So the definite integral of course, is the indefinite integral evaluated from 0 to b. Evaluated from 0 to b. And so we make that calculation. We're not ready to take the limit yet because we don't know what we're taking the limit of. Well, when we evaluate at b, we have natural log of e to the power of b plus 1 minus the natural log we evaluated at 0, so we have e to the 0 plus 1. Now, of course, e to the 0 is just 1, and so we're really subtracting the natural log of 2 there, aren't we? So we have a limit as b approaches infinity of the natural log of e to the b plus 1 minus the natural log of 2. Well, of course, the limit of a difference is the difference of limits, and the limit of natural log of 2, which is just a constant, it doesn't really matter what b is doing at all. So the limit of natural log of 2 is just natural log of 2. The real issue becomes the limit of this first expression. And so we're taking the natural log of something, and just knowing what the natural log graph looks like, say the natural log graph will look like this, won't it? Okay. Now, what's going on? Well, we're letting b get larger and larger. So e to the b, since b is positive, e to the b is a value that's getting larger and larger. And of course, plus 1 is getting larger and larger. And so as b gets larger and larger, e to the b plus 1 does. And as e to the b plus 1 gets larger and larger, then the natural log gets larger and larger. In other words, the limit of natural log of e to the b plus 1 is infinity. And of course, as that gets large, I say is infinity, then really and truly, the natural log, the limit of the whole expression is infinity. And so that tells us then that this integral diverges. The integral diverges. So it's not a finite sum. Let's continue with the second example. Okay, here we have an integral from negative infinity to 0. And the 0 that's common in both of these integrals is just coincidental. We don't really need to be concerned about the fact that we're always going to have a 0 as one of these limits of integration. But anyway, integral from negative infinity to 0 of 1 over 1 plus x squared. We're just to either evaluate it, find its value, its finite value, or otherwise state that it diverges. So we go through the same process, a similar process that we went through before, except now our upper limit of integration is a constant, is our lower limit of integration that we're concerned about. And so the idea, remember, is that whatever this graph looks like, we actually need to choose some value a that's bigger than infinity, negative infinity, and then let a go toward negative infinity. So here's what I'm saying. We start out to evaluate from negative infinity to 0 of, 1 over 1 plus x squared with respect to x. Now, obviously, we can't evaluate at negative infinity. So what we do is we replace negative infinity with some constant, and I'm calling that a, and the 0 is not a problem. So we're going to integrate from a to 0, but that's not really the value we want. We want to know the value of the integral from negative infinity to 0. So we calculate that one value, and we look at the result we get there, and we let our a get smaller and smaller by going to negative infinity, and that should give us our result. So now we're concerned about the indefinite integral of 1 over 1 plus x squared. And isn't this one of the inverse tangent forms? Isn't this an inverse tangent form? Won't that be equal to the inverse tangent of x. Remember, sometimes, plus our constant integration, sometimes instead of showing inverse tangent, depends on the book that we're using. Sometimes that's called arc tangent, okay? But nevertheless, the integral of 1 over 1 plus x squared is the inverse tangent of x. And you can verify that, but that's something that we should know by now. We will certainly be tested. We have been tested and will be tested again over that. So anyway, the integral of 1 over 1 plus x squared is the inverse tangent of x, and we're evaluating that from a to 0. Of course, taking the limit of that result. Well, here we go. The limit as a approaches negative infinity of, when we do this evaluation, we'll have the inverse tangent of 0 minus the inverse tangent of a. Now, what's the inverse tangent of 0? Remember, the inverse tangent we can think of as a real number, but we can think of it as a angle in radians, and it's the angle that when we take the tangent of it, we get 0. And we don't have to get out our calculator to do this. What angle can we take the tangent of and get 0, and the angle itself is 0, but we're doing this in radians. So this is really the limit as a approaches negative infinity of 0 minus the inverse tangent of a. Well, we're not out of the woods here yet. Of course, that's just the limit as a approaches negative infinity of the negative of the inverse tangent of a. Now, here it becomes very important for us to be able to rely on some old information. And one of those pieces of information that we may need in the future, we certainly need now, is what does the graph of the inverse tangent function look like? Well, remember, it's the inverse of the tangent function, except it's restricted to one single period of the inverse tangent function. And let me just sketch it in here. And if you don't know this, then you need to go review some trigonometry and convince yourself that you understand why it looks the way it does. So when we're talking about the tangent function, we have multiple periods, and in one cycle it looks like that. Now we're inversing that, which means we're replacing the x-axis and the y-axis with each other. And when we do that, then we get a graph that looks like this. But we're only using one of the cycles, okay, for an inverse. Now, where are these asymptotes in the graph of the tangent function? On the graph of the tangent function, this is at pi over 2, and this is at negative pi over 2. Well, in this problem, as you see, we're asked to evaluate the integral from negative infinity to 0 of 1 over 1 plus x squared with respect to x, or state that the integral diverges. And we don't know about divergence or convergence until we start actually trying to do the calculation. So we begin this time, so we're going to evaluate negative infinity to 0 of 1 over 1 plus x squared with respect to x. And what we recognize is we can't evaluate an integral at a negative infinity. So what we do is we replace that negative infinity with a constant. And I'm creating a constant, calling it a. Now I'll kind of use a and b. And if the b is, if it's the lower value, then I call it a. If it's the upper value, I call it b. And here we have a 0 there. Okay, so that's really not what we're trying to calculate. We know that's going to be a finite value. We calculate that and say, okay, here it is from some particular a that's smaller than 0. But what we really want to know is what does it look like when that a gets smaller and smaller? That a goes to negative infinity. So kind of what we're doing here is we're thinking whatever this graph looks like, and by the way, this is what the graph looks like, more or less. And we're saying, okay, we're choosing some A here, we're going to 0 here, but we really don't want A. We've got to let A go further and further to the left. And so that's what we're saying is A is approaching negative infinity. First going to calculate it for a finite value, and then we're saying what happens is A gets smaller and smaller as it approaches negative infinity. Okay, so now we're in a position that all we have to do is evaluate. First, we have to evaluate the integral of 1 over 1 plus x squared. And I hope that you'll recognize, because we've just been through this, this is the inverse tangent of x. The integral of 1 over 1 plus x squared, the indefinite integral of 1 over 1 plus x squared, is the inverse tangent of x. Of course, plus an appropriate constant if we're talking about an indefinite integral only. Now remember, in some books, that's called arctangent of x. It just depends on the book. So, but we're evaluating that from the constant a to the constant 0, aren't we? So as we go through here, let's see. We're going to find a limit in a moment, but we haven't figured out what we're taking the limit of. We evaluate inverse tangent at 0 and then at a. So inverse tangent of 0, subtract inverse tangent of a. Now, what's the inverse tangent of 0? Try without your calculator. It's the angle that we can take the tangent of and get a result of 0. Well, that value would be 0, right? The tangent of 0 is 0, so the inverse tangent of 0 is 0. So this becomes the limit then as a approaches negative infinity of 0 minus inverse tangent of a. Now, obviously, we can clean that up a bit and say that's the limit as a approaches negative infinity of simply the opposite of the inverse tangent of a. So if we could calculate the limit of the inverse tangent of a as a approaches negative infinity, then we ought to be able to complete this. So here's what we need to do next. We need to, and I hope that from trigonometry you recognize this. Remember, y equal the tangent of x. Because it's a cyclic function, isn't it? And so it's got multiple cycles, that is, but when we're interested, it's got multiple cycles like this. But when we're dealing with inverses, we've got to pick a single cycle where the function is 1-to-1. That is, it has an inverse. That is, for each y, there's only one x. And so we pick the cycle, if you will, the period, in this case, that goes from an x value of negative pi over 2 to an x value of pi over 2. Okay, and those are those asymptotes. Now remember what the inverse tangent would look like. It'd be the graph of the inverse tangent function would be the inverse of that particular function. So we replace the y-axis with the positive x-axis and the positive x-axis with the positive y-axis. So it's kind of a flip and a twist. But if you don't remember this, you do need to kind of review your trigonometry so that you know what this graph is going to look like. Because knowing what this graph looks like is a critical issue here. Well, what's going to happen is when we do this inverse, then those vertical asymptotes end up being horizontal asymptotes. So this horizontal asymptote is at the y value of negative 1/2, and this horizontal asymptote is at the y value positive 1/2. And if you recall then what this graph is going to look like, when we look at the inverse, it's going to look like this. Okay? So we can use that graph to decide what the inverse tangent of A, the limit of the inverse tangent of A is as A goes to negative infinity. So our A here is like the x's, isn't it? As A goes further, or X, A goes further and further to the left towards negative infinity. This is A approaching negative infinity, isn't it? Then what's happening to the Y value? Well, it's getting closer and closer and closer to the value negative pi over 2. So the limit of the negative of the inverse tangent of A as A approaches negative infinity is the negative of negative pi over 2. Because that's the value of Y that the graph is getting closer and closer to down here, isn't it? And so that result, of course, is positive pi over 2. So if you know this geometric representation that we're talking about, we'll kind of throw this back to what we were doing. If we look at the original graph, here, say up here, of y is equal to 1 over 1 plus x squared, and we evaluated the integral from negative infinity to 0, well, that really basically what that means is we've calculated the area of this unbounded region, and that area is pi over 2. Well, let's look at a couple of other examples, and there's some interesting things that we can do that has some surprising results. So we'll continue on the next page. This is a very interesting problem, and one that has surprising results. It kind of gives you the idea that you can't always make assumptions with things precise like mathematics, because sometimes we're surprised. Well, here's the problem. First, we're to consider a region bounded by the graphs of y equal 1 over x and y equals 0 on the interval from 1 to infinity. And part A, well, I'll tell you part B in a moment, part A is to show that the area of the region described is infinite. Well, let's just roughly talk about what region we're discussing here. X-axis, y-axis. Let's suppose, just so we have something to refer to, here is 1 for y, and so here is 1 for x, roughly. Okay, and so now we're considering from x values 1 to infinity. Okay, let's keep that in mind. That's the only part of the graph that we need to look at. And it's bounded by y equal 1 over x. Well, y equal 1 over x, when x is 1, y is 1. And of course, as x gets bigger, y gets smaller. So for instance, if x is 2, y is 1/2. And if x is 3, y is 1/3, and so on. So this graph is going to look something like this. Okay? Something like this. I probably should be a little more precise. And so we're interested in, from x equal 1, and bounded by y equals 0, which is the x-axis. So this is the region we're talking about. So it's unbounded to the right. What's the area of that region? And the problem already tells us the answer. It's infinite. But we're going to go through the process and figure that out. Now, B part, you can see here. Take that region described in part A, or described above, revolve that infinite region about the x-axis. Okay? And when we do that, it creates a solid, and it tells us to show that that solid has a finite volume. That infinite region creates a finite volume. And when we do that solid that we're discussing, it has the name Gabriel's horn. That's what it's been called. Okay. Of course, if you know about the Archangel Gabriel, and there's no religion meant in this. It's just to discuss what's going on. It's a name. So here's -1, here's +1. here's a positive 1. So when we rotate that about the x-axis, just to try to give a little idea here, and it's going to look something like this. Okay. And so this is an infinite, whoops, it doesn't stop. Okay, I've got that arrowhead that it's hard to see. It's an infinitely long solid that has a finite volume. Okay, Gabriel's horn is an infinitely long solid. So let's go about and start with part A. And I'll start here. We'll probably have to continue to the next page just to finish A. But when we're calculating, so when we're doing a calculation of a area, and the area is all above the x-axis, it's really pretty straightforward, isn't it? Part A, area is equal to. Well, in this case, the area is the integral starting at 1, but going forever to the right, from 1 to infinity. And what are we integrating? 1 over x with respect to x. So we set up our limit. Okay, what's our limit going to look like? Well, we're integrating from 1 to non-infinity, since we can't do that, to 1 to some constant b that's bigger than 1. So we're thinking of that b being out here, and we're going to make the b go further and further to the right. The way we do that is then we take the limit as b goes to positive infinity. And we're still integrating, of course, 1 over x. Well, what is the integral of 1 over x? Well, you know, if it's not drilled into our head already, the integral of 1 over x is the same as the integral of x to the negative 1. And so when we're integrating, what do? We increase the power. Oh, stupid here. What am I saying? What's the, you know, even I make silly mistakes. The integral of 1 over x with respect to x, and of course our x is positive here, it's just the natural log of the absolute value of x. But in the x's that we're talking, well, we'll just write it that way. Okay. Because they're constant integration. So here's what we have. The limit as b approaches infinity of the integral of 1 over x with respect to x evaluated from 1 to b. Well, the integral of 1 over x is the natural log of the absolute value of x. And I am going to say here, we don't really need absolute value because our 1 is positive and our b is also bigger than 1, so it's positive. So I'm just going to say natural log of x, and we're evaluating from 1 to b. So when we do that evaluation, trying to squeeze things in here, then we're going to have the natural log of b minus the natural log of 1. Now, of course, the natural log of 1 is 0, so what we really have here is nothing more than the limit as b approaches infinity of the natural log of b. Well, as b gets larger and larger, so does the natural log of b. So the limit of the natural log of b as b goes to infinity is, in fact, infinity. And that's what we were really asked to show here. We'd say that the integral diverges, but we're specifically looking here to say that the area involved, the area of the region that we've diagrammed, is infinite. Okay? So part B on the next page. Okay, now we're to show that the solid of revolution that's formed when we do this has a finite volume. So let me just kind of sketch in again so we have something to think about. So here's one, and we have this solid that looks like this. Of course, it goes infinitely. And we want to calculate the volume of that solid. Well, we're really going to use here the disk method. So we think about one little piece of this, okay, and think of that disk that we would have when we take that one little piece, okay, and it would look something like this, wouldn't it? And of course, this is the dimension dx, as we've talked about before. And what's the volume of that disk? Well, the volume of that disk is pi times r squared. And r is the distance along here. And that distance, of course, that r in this case, that distance is nothing more than our functional value 1 over x. So it's pi times 1 over x squared, or pi times, when we square 1 over x, we get 1 over x squared, don't we? So to calculate this volume, we're going to integrate from 1 to infinity. And we're integrating pi times 1 over x squared with respect to x. That's the integration we need to do to create the volume of that, to calculate the volume of that solid. Well, here we are again. We need to set up the limit because we have an improper integral here. So we're going to find the limit. Now, what are we going to do? We're going to replace our infinity with some value b. And we're going to find the limit then as b goes to infinity. Now, what are we calculating? The integral of pi times 1 over x squared with respect to x. Now, in this definite integral that we can actually calculate, that pi is a constant, isn't it? So we'll factor that pi out and just worry about the integral from 1 to b of 1 over x squared. Well, the integral of 1 over x squared you can easily determine. Okay, the integral of 1 over x squared is negative 1 over x. You can determine that without a great deal of trouble. So we're evaluating that from 1 to b. Well, as we do this evaluation, and by the way, that pi could actually be factored out too, because the limit of a constant times something is just, of course, the constant times the limit. So we can factor that pi out further. And what are we doing? Well, we're going to first evaluate at b, so we have negative 1 over b, subtract, evaluate at 1, negative 1 over 1. Now, as the dust settles here, I'm going to write that a little differently. A negative of negative 1 is a positive 1, so I'm going to put that positive 1 minus 1 over b. Whoops, I see I left off b approaches infinity. Well, now this is simple to calculate. Here's our pi value, factor in front, and the limit of 1 minus 1 over b as b goes to infinity, then that's 1 minus 0, isn't it? So the limit here is pi times 1, or pi. So the volume of Gabriel's horn is pi. So the volume of this solid created by revolving an unbounded infinite area about the x-axis gives us a finite volume. That's just amazing, isn't it? Okay, well, let's turn to the other types. We've really looked at several examples here of improper integrals for one of the, we have one of the limits of integration is infinity, so an infinite integral, if you will. Let's turn our attention to the other type of improper integral.